Another way that, oh wait, sorry. So carbon dioxide, remember one of the things we saw a minute ago is carbon dioxide is a greenhouse gas, and actually that will increase temperatures, and the warmer temperatures will increase water evaporation in the precipitation cycle. But the problem with it is that we have the amount of carbon dioxide that is not going down because of precipitation. The amount of carbon dioxide actually continues to increase. We're throwing Mother Nature a monkey wrench, basically. So what this is looking not at carbon dioxide, but it's looking at surface temperatures from 1880 to 2000. Okay, and it may not seem like much, but up here we've got an increase worldwide of a surface temperature increasing 0.6 degrees Celsius. Okay, and you're like, 0.6 degrees? Well, I'm fine with that. Okay, but it has consequences. And I have a slide to kind of show you what global warming, what's been going on behind the scenes from global warming. But this slide, I like it. It's a figure from your textbook. These two graphs kind of look alike. They spike at the same time. They go down at the same time. Okay. They actually, the top one, the yellow one, is our surface temperatures. But notice that it goes back like 800,000 years ago. So that's what that 800 is. 800,000 years ago here on Earth. What was the temperature? Okay. And what was the carbon dioxide in the atmosphere? Okay. And it goes down and up and down. So temperature, carbon dioxide goes up, temperature goes up. Okay. And you might be like, well, how do we know this that long ago? And it's called proxy data. That's probably what I would call it. And so that's a whole other story. So here then we have kind of with regard to carbon dioxide, you see that big jump right there? Sometimes they call it the hockey stick model. So basically, this right here, this jump in carbon dioxide, that is human activity. Okay? So not to say carbon dioxide go up, and it has for 800,000 years. Okay? So kind of related to that, not going back, hundreds of thousands of years, but this is going back to the year 1960 to not quite the present. Actually, the present, I remember it was maybe a year ago when we went in excess of 400 parts per million. That's a big, hairy deal. So that's carbon dioxide going up. It's taken in Hawaii, and actually they were in the news maybe a year ago, and it was like, well, who's going to fund these guys? Who's going to keep paying for this to go on? And I don't know. I think it should go on, but so that's that. So another thing that's been in the news is the hurricane, right? Like, okay. So if you've been listening, like I have a little bit, not a whole lot, but they talk about what is the hurricane going to do. And what they do is they have different computer models that they put in conditions of the atmosphere, and then they let the computer crunch, well, what's it going to do? Okay. So there's these different computer models, right, that's going to say and so depending upon which computer model you pick, you might see it do something different. Well, that's kind of what this slide is. It's basically saying, let's look at the temperatures, the surface temperatures, okay, from 1860 to the future. Okay, and then let's go ahead and predict what the future is going to be. Okay, actually, these models are looking at real data of carbon dioxide and real surface temperatures. And I guess I would draw your attention to the purple and the black one, how well they agree. Okay, if you use a computer model that factors in carbon dioxide that humans are adding to the atmosphere, you get that agreement. Okay, this one, you don't get that agreement. Okay, so that's real data versus the computer-generated program if you consider the influence of human activity. So, like I said, who cares? 0.6 degrees Celsius, who cares? Well, Greenland people care. Okay, so the climate in Greenland has changed What used to be an ice sheet, it's over here in white, in 1979, you can see the extent of the ice sheet. In 2012, you can see the extent of the ice sheet, for example. So melting glacial ice. Rising sea levels, actually, I don't know if it'll go very far, but people who live on little islands where basically as the glaciers melt, they add water to the oceans, and so the sea levels rise, okay? People who live on these little islands are kind of wanting some help because their island is disappearing, okay? So, with increasing surface temperatures, we could end up with more intense storms. Now, I've heard kind of both sides of that. So, but one thing about it is, for instance, little nasty things that used to grow or be only able to thrive in warm conditions near the equator, well, since it's getting warmer farther from the equator, those things can migrate towards the poles. Fire ants, okay, my family, my in-laws live in Mississippi. Fire ants migrating, okay, because it's warmer where it not used to be so warm, okay. Of course, the polar bears lose their habitats. So to kind of summarize what we've talked about in this chapter so far, we talked about the different terrestrial objects, including the moon, okay, and we said size matters, okay. We said that the larger ones retain their heat, okay, and the smaller ones cool and are not geologically active. Just a kind of summary slide. I'm glad we're at. All right. So let's just start the next chapter. So chapter 7 assignment will be due on Monday. And chapter 8 is longer. All right. So, looks like Saturn maybe? When we think of rings, a planet with rings, we think of Saturn, but all of the gaseous planets actually have rings. Okay. So the gaseous planets can be kind of thought of as kind of in pairs, where basically you have the orange ones, okay, and then you have the blue ones. And the reason they got so large is that they were actually on the cool side of the frost line. And on the cool side of the frost line, you wouldn't have the gases hydrogen and helium condensing, but you would have water, methane, and ammonia actually coming out of its gaseous state to become part of the planet. And then we said that the planet continued to grow because then actually when it had a certain amount of mass, the gases then they wouldn't condense, but they would hang around. So Jupiter is by far the largest of the gaseous planets, and actually there's some stats underneath this in this figure. Okay, with regard to mass, Jupiter is running 318 times the mass of the Earth, okay, versus 95 times the mass of the Earth for Saturn. So if anybody asks you what do these all have in common, here's a list of 4 things. I think we've already talked about some of these. What do they have in common? Actually, they have bands. We usually think of Jupiter as having the bands and Saturn as having the rings. They all have lots of moons, okay? And they all are just like they have swallowed terrestrial planets. They all have a rocky core. So, density-wise, anytime somebody talks about density, and we do hear in astronomy, often I'll talk about density, basically they're saying how squished together the matter is, or how fluffy or how compact the matter is. So Jupiter is significantly more dense than Saturn, and it kind of has to do with that there's more matter that Jupiter basically kind of squishes down, okay, compared to Saturn. So Jupiter is more dense than Saturn. In fact, we said that Saturn would float in a bathtub of water. So if you, here on Earth, you can take a gas, which I think we talked a little bit about gases in here, but basically gases are really sparse. They're like cats. It's hard to corral gas particles. And you can take a gas and squish it down, and you can make it turn into a liquid just from pressure. Okay? You can take a gas and squish it down, and gas will turn into a liquid, then gas will turn into a solid. For instance, the dry ice that you might buy at the store to cool things down, dry ice is carbon dioxide that basically has been pressurized and cooled. Okay, so it's possible. So with that in mind then, if we look at kind of the interior of Jupiter, okay, we actually kind of see that sort of phenomenon going on. So the gas giants are mostly hydrogen and helium. And actually, anytime you go towards the center of a planet or a star, pressure increases. So here we have hydrogen that's gas, pressure increases. Here we have hydrogen that's a liquid, pressure increases. Actually, here we have hydrogen that's behaving like something we call metallic hydrogen. Okay. Down here in the core of, in the center of Jupiter, we actually then, remember we talked about planetary differentiation where heavy things settle and light things rise? So I keep talking about it's like it swallowed a terrestrial planet, and actually that's the terrestrial planet here in the center. Okay. So that's Jupiter, and Saturn is very similar, not surprising. Okay. So we have Jupiter and Saturn and Uranus and Neptune down here. Now I thought of you guys, somebody said something about that little spacecraft falling through Jupiter. Actually, this slide mentions it by name, so Galileo. And as it fell through, it transmitted for a while. That's kind of, have you guys ever heard that story about the guillotine person, and like they did an experiment where, I don't know, I'll blink as many times as I can, and so you know that I don't know. Anyway, it's kind of disgusting. That reminds me of Galileo. All right. So between the orange planets and the blue planets, there are some differences. Okay. If we remember the Earth, that the Earth has a magnetic field, and the reason the Earth has a magnetic field is because it's ooey gooey in the center. It has some sort of liquid that can jostle around, carrying charges as it rotates. Okay, so that creates a magnetic field. Well, actually, these gas giants, they have magnetic fields. Okay, they are rotating very quickly. I think, was it like 10 hours or something, 9 hours? It takes Jupiter, which is humongous, to complete one rotation on its orbit. In its rotation.
Question.
What's that? Yeah.
Okay. I don't know why I thought of this, but it made me think. So.
Does that do with the guillotine? Okay.
So like black holes, almost really random, but like, okay, so they send ships, like satellites through the space, right, to take pictures of planets. Are there black holes like anywhere in between? Are those like way out?
Black holes, there can be, theoretically, there are actually can be little tiny black holes that were created basically at the beginning of the universe. So you can actually stumble into a black hole, but it's very small. But
I was just thinking, like, you know, if you're sending like the satellite thing through, it's like, you know, you gotta make sure you're on that plane that hit the planet right. But what if you like go off and then just boom, like oops.
So sorry.
Like, would you be able to see it? Like, can you see it? Is it like black out there? Or like?
The black hole, and we'll talk kind of about it coming in a different unit. Like if a spacecraft fell into a black hole,
Yeah, would I be able to see where it's like it already went into one, or like be able to see it?
What show is that? Stargate Universe, like where they actually send the probe and it comes back, right? Okay. But it would transmit for a while, and then black holes, the only reason they're called black is basically once you get too close to the singularity, you cannot escape, and like light cannot escape. It can't. So that's what makes it black.
Gotcha. Oh, gotcha.
Yeah.
Okay. I don't know, I was just thinking.
Yeah.
Black holes are scary to think about.
Black holes are scary to think about.
Kind of freaking out a little bit.
Yeah,
I
it's
just like I
so
gotta say
scary.
something.
So I don't know if that helped you any, but yeah, still freaky.
I don't know if they're sitting around in our like planets' orbits and stuff.
No, they aren't. They are. I kind of teased about they're theoretically they could be anywhere, but no, they aren't. No, they
Say
aren't.
what they like pull us in kind of thing.
They wouldn't pull us in as long as we're far enough away. But if we got close enough, then their gravitational influence would affect us. And that actually, right then and of itself, is why we know they're not out there. Because it's kind of cool, because if this is a black hole, and basically you have light over here, okay, that should come right towards me. Actually, the light will go like this. It'll be like, it won't be sucked, but actually it's like, it's a gravity well, not a suck, but the light will be bent. And so the fact that we don't see light doing funky things means that there's really, in the immediate place, no black holes. But we do see light being bent other places, and that's like, oh my gosh, there's a black hole there. Don't go there.
What's
Yeah.
in the black holes?
What's that?
What is in the black holes?
What's in the black holes? Well, you know how, like, here we talk about stuff is made of atoms, you know, and we talk about atoms. So a black hole is basically, and we talked about density today. You know, basically density is how kind of fluffy or how compact something is. Basically what's happened with a black hole is that you have taken matter and basically you're making atoms coexist in the same spot, sort of. You're squishing the matter down. To get a black hole, all you got to do is squish matter down. And so basically you have atoms that have to be at the same place, and they basically turn from regular atoms into something else. It's very, 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 very dense. And so a black hole is made up of just this exotic sort of, really? Black holes, according to Stephen Hawking, black holes actually do evaporate over time. They eventually kind of ding, 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 they get smaller and smaller because they're nothing. Okay, so I don't know if that answered your question, but what is it? That's what it is. It's like particle soup that they're not atoms, they're just stuff. Yeah. Don't go there.
So if you go in and it decomposes or whatever, are you just like, I'm out? Like, is that how that works?
Yeah, if you go in being like a person or whatever, you are just, your atoms basically are converted into black hole stuff.
Whatever
And
that black hole is.
black hole stuff, and you just become part of the,
Oh, gotcha.
yeah. And that reminds me of like, the cube, what do they call that? In Star Trek, what's the,
What you talking about?
the Borg. It's like the Borg, you're just kind of like a collective. But you're like a collective. It's not good. That's good questions, though. It's interesting. All right. So Jupiter, Jupiter, actually has a magnetic field. Not so surprising, because it rotates very quickly, and it definitely has liquid charges that can spin around and create a magnetic field. So this ghosty looking thing is Jupiter's magnetic field. And Jupiter's really big, right? So, but kind of drawn to scale on here is the extent of his magnetic field. So look at the tiny Jupiter there. What's that?
So it's like, your magnetic field's crazy looking.
It is crazy
Does it move
looking.
so fast?
What's that? Yeah, that's because it's so big and it moves so fast. Yep. Yep. So you know on Earth how we have the northern and the southern lights, okay? Kind of the glow where the basically charged particles from the sun are kind of filtering through our magnetic poles. So also Jupiter does. All right. So I think that's a good place to stop it today. And we'll pick up here on Monday.